Imagine the scene. It is November 1918, and engineers throughout the European continent are confronted with an intractable conundrum. The Great War has finally concluded, yet its profound lessons are indelibly etched into every churned-up battlefield, from the blood-soaked earth of Verdun to the desolate expanse of the Somme. A stark realization has emerged. Mere wheeled vehicles are no longer sufficient to secure victory in modern warfare. Conventional trucks inevitably succumb to treacherous terrain, tanks frequently suffer mechanical failures, and somehow, armies must find a way to transport personnel and heavy ordnance across landscapes that eerily resemble the pockmarked surface of the moon. It is precisely at this juncture, in the peculiar confluence of two seemingly incompatible ideas that nonetheless must coalesce, that our narrative truly begins. The groundbreaking concept of the half-track did not materialize spontaneously from thin air. Its origins trace back to 1915, when a gifted French engineer named Adolphe Cagrès was employed by Tsar Nicholas II in Russia. His critical mission involved ensuring the continued mobility of the imperial family's automobiles as they navigated the unforgiving expanses of Siberian snow. Cagrès' ingenious solution was to replace the standard rear wheels with resilient, flexible rubber tracks, while strategically retaining the front wheels for precise steering control. This approach was not only elegantly simple, but also remarkably effective in practice. By 1919, the prominent French automotive manufacturer Citroën had acquired Cagrès' patents and commenced production of the innovative Cagrès-Hinton system, thereby unequivocally demonstrating that this hybrid vehicle design possessed the capability to conquer challenging terrains that had previously proven insurmountable for purely wheeled vehicles. However, at this early stage, military applications were not yet under consideration. The primary objective was simply to facilitate reliable transport from one location to another when confronted with nature's formidable obstacles. Then arrived the decade of the 1920s, a period when military strategists began to pose increasingly difficult and probing questions. While tanks undeniably offered immense destructive power, their operational speed was agonizingly slow. The formidable British Mark V, for instance, could barely achieve a paltry 4 miles per hour on an exceptionally favorable day. Conversely, traditional trucks, though swift on paved surfaces, became utterly useless the moment they ventured off established roads. Infantry units, astonishingly, continued to advance on foot, a method of movement unchanged since the era of Napoleon, which inevitably meant that mechanized armored divisions would surge ahead only to be compelled to halt, patiently awaiting the arrival of the rifle-carrying foot soldiers. After 2 or 3 paragraphs, ask US to stay with US and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Even Germany, despite its recent defeat in the global conflict, was already meticulously outlining innovative design concepts. The Soviet Union was actively engaged in various experimental programs. Even the United States, a nation that had only marginally deployed tanks during the First World War, began to diligently explore novel designs at its renowned Rock Island arsenal. The profound allure of the half-track lay in its audacious engineering compromise. It offered approximately 70% of a tank's formidable off-road capabilities, while concurrently retaining an impressive 80% of a truck's crucial speed and fundamental mechanical simplicity. The presence of front wheels afforded surprisingly effective steering without the need for complex and often problematic track braking systems. Furthermore, the rear track sufficiently distributed the vehicle's substantial weight across diverse surfaces such as mud, sand, or snow. Crucially, because the vehicle's propulsion did not rely on powering all 4 corners with tracks, the entire assembly was inherently lighter, more economical to produce, and significantly easier to maintain than a full-fledged tank. In 1931, the United States Army conducted trials with the Cunningham T-1, a vehicle that was essentially a conventional truck retrofitted with tracks on its rear axle. Its appearance was admittedly unconventional, even somewhat ludicrous. Yet, this seemingly absurd contraption effortlessly traversed trenches that would have completely immobilized and swallowed standard trucks. By the mid-1930s, the grim realities of global politics were rapidly crystallizing. Germany, in blatant defiance of the Treaty of Versailles, was aggressively rearming. Japan was relentlessly expanding its influence into China with formidable mechanized columns. The Spanish Civil War, raging from 1936 to 1939, served as a crucial proving ground where all observing powers assimilated the same harsh truth. Modern warfare unequivocally demanded that infantry forces maintain pace with armored units, and, moreover, these soldiers needed to arrive at the point of engagement prepared to fight, not utterly exhausted from arduous marches spanning 20 miles or more. The half-track had transcended its initial status as merely a clever invention. It was rapidly transforming into an indispensable military necessity. Engineers in industrial centers such as Detroit, Stuttgart, and Moscow found themselves engaged in an intense, undeclared race to resolve the same intricate puzzle: how to construct a vehicle that could simultaneously engage in combat like a tank, transport material like a truck, and deliver firepower akin to artillery, all while adhering to a production cost low enough to enable the manufacture of thousands of units. This pivotal question would ultimately define the very machines that would roll into Poland, traverse the battlefields of France, penetrate the deserts of North Africa, and eventually extend their operational reach across half the globe. The era of the hybrid warrior, poised for global conflict, was undeniably at hand. The American approach to developing the half-track mirrored their characteristic methodology for virtually every major industrial challenge in the 1930s, an unwavering focus on mass production from the very outset. While their European counterparts were meticulously crafting bespoke, highly specialized solutions, engineers at the White Motor Company in Cleveland and Autocar in Pennsylvania were already conceptualizing vast assembly lines designed to churn out vehicles by the thousands. This strategic foresight culminated in the renowned M2 and M3 half-track family, machines that, despite their outwardly stark and brutally simple appearance, concealed a truly ingenious array of engineering solutions beneath their utilitarian, boxy steel panels. Let us commence with the vital power plant. White Motor ultimately selected the Hercules JXT inline six-cylinder engine, a robust 386 cubic inch gasoline motor that generated a respectable 147 horsepower at 2,800 revolutions per minute. While this figure may not appear particularly impressive when juxtaposed with contemporary engines, its crucial advantages were its unwavering reliability, its capacity for rapid manufacturing, and the fact that mechanics, already familiar with civilian truck engines, possessed an inherent understanding of its maintenance and repair. The engine was conventionally positioned at the front, in typical truck fashion, which facilitated straightforward thermal management and permitted easy access for servicing without necessitating the arduous disassembly of the entire vehicle. On paved roads, the half-track could achieve a maximum speed of 45 miles per hour, which typically decreased to approximately 25 miles per hour when traversing challenging cross-country terrain, a speed ample enough to maintain formation with tank columns, yet not so excessive as to render the ride a jarring, bone-rattling ordeal for the 10 infantry soldiers accommodated in the rear compartment. The transmission system was where the White engineers truly demonstrated their exceptional skill and justified their remuneration. They meticulously developed a 4-speed manual gearbox complemented by a 2-speed transfer case, thereby providing the driver with a comprehensive total of 8 forward gears, in addition to 2 reverse gears. This extensive range allowed the vehicle to laboriously ascend a formidable 60% grade in first low gear or to effortlessly cruise at highway speeds in fourth high. Power was efficiently routed from the transmission to a front axle, which drove the wheels, and a separate drive shaft extended rearward to engage the track assembly. The front wheels retained their conventional pivoting capability for steering, but here lay a crucial innovation. The driver was also equipped with brake pedals that could independently slow individual tracks, enabling significantly sharper turns than could be achieved by the front wheels alone. While mastering this intricate system required considerable skill, experienced drivers could effectively pivot these vehicles almost in place. Now, let us examine the track system itself. This component truly exemplified American pragmatism. In stark contrast to the metallic links typically found on tank treads, the M2 and M3 utilized innovative rubber block tracks meticulously developed by the Firestone Tire and Rubber Company. Each track was ingeniously constructed from steel cable embedded within resilient rubber, with 110 individual rubber blocks vulcanized onto the cable. These blocks, roughly 5 inches wide, were specifically contoured to maximize grip on dirt, mud, or snow. The inherent brilliance of this design was threefold. Firstly, rubber was considerably quieter than the incessant clanking of metal on metal, a factor of significant tactical importance for covert movement. Secondly, rubber exhibited superior durability on paved roads, avoiding the rapid wear and tear that would quickly degrade highways or prematurely exhaust metallic tracks within a mere 100 miles. Thirdly, in the event of damage to a section, individual blocks could be replaced in the field, obviating the far more complex and time-consuming process of swapping entire track assemblies. The suspension system was a modified vertical volute spring suspension. Fundamentally, this involved large coil springs mounted vertically behind each of the 4 road wheels on every track assembly. As the vehicle navigated over obstacles, these springs effectively compressed and absorbed the ensuing shock. Was the ride inherently smooth? Not particularly. Riding in the rear of an M3 over rugged terrain was often likened to being inside a cement mixer, yet its fundamental efficacy was undeniable. It was straightforward to maintain, and, most importantly, it efficiently distributed the vehicle's substantial 20,000-pound combat weight across a sufficient surface area to maintain ground pressure at approximately 10 pounds per square inch. For context, a fully loaded conventional truck might exert a ground pressure of 40 psi, a stark difference that elucidates why trucks often sank in mud while half-tracks consistently maintained their mobility. Production surged with astonishing rapidity once America officially entered the war in December 1941. The manufacturing facilities of White Motor, Autocar, and Diamond T were collectively churning out an impressive 500 half-tracks per month by mid-1942, a figure that escalated dramatically to 1,500 units per month by 1943. Total production, encompassing all variants, ultimately exceeded 41,000 units by the conclusion of 1945. This phenomenal output underscores the genius of the American approach. These machines, while perhaps not the absolute pinnacle of half-track design, were unequivocally good enough, and their sheer numerical abundance rolling off assembly lines proved utterly indispensable precisely when Allied armies required them most urgently. While American engineers were meticulously designing for unparalleled mass production, their German counterparts were consumed by an entirely different obsession, achieving technical perfection, irrespective of the associated costs. The Sonderkraftfahrzeug 251 SD, KFZ. 251, more commonly referred to as the SD, KFZ. 251 or simply Hanomag, after its primary manufacturer, epitomized a diametrically opposed philosophical approach, where the Americans pragmatically declared, "Good enough is good enough." The Germans insisted that every single mechanical component should be engineered to its absolute theoretical limit. This uncompromising dedication to excellence rendered their half-tracks phenomenally capable in performance, but concurrently made them absurdly intricate and costly to construct. At the very core of the SD, KFZ 251 was a Maybach HL42 six-cylinder gasoline engine, which produced a comparatively modest 100 horsepower, less than its American Hercules counterpart. However, this is where the narrative becomes particularly intriguing. Maybach was the very same prestigious company responsible for manufacturing the powerful engines that propelled the formidable Tiger and Panther tanks. Consequently, this was no mere truck motor repurposed for military service. The HL42 was meticulously engineered specifically for tracked vehicles, with scrupulous attention paid to optimizing torque delivery at lower RPMs. This sophisticated engine propelled the 8.5-ton vehicle to a road speed of 53 km per hour, actually faster than the American M3, although their respective cross-country performances remained remarkably similar, hovering around 20 to 25 km per hour. The German engine operated at cooler temperatures and with greater fuel efficiency than its American counterpart, but demanded more frequent and specialized maintenance, relying on precision-engineered parts that required significantly longer manufacturing times. German transmission engineering frequently bordered on what many would consider over-engineering. The SD, KFZ 251 incorporated a Maybach Varirex 128H preselector gearbox, boasting an astonishing 7 forward speeds and 3 reverse gears. Allow the detail to fully register. 7 forward gears. The driver would pre-select the next desired gear using a dedicated lever, then merely tap the clutch pedal, and the transmission would execute the shift automatically via a sophisticated vacuum system. When this intricate system functioned as intended, it offered a smoother and faster shifting experience than the manual transmissions found in American vehicles. However, when it inevitably malfunctioned, which regrettably occurred with greater frequency, it necessitated the expertise of a specialized mechanic and replacement parts that could often take weeks to procure. This encapsulates the German half-track story in miniature, technically superior in concept, yet logistically nightmarish in practice. The German SD, KFZ 251 half-track, while mechanically sophisticated, presented an operationally challenging and complex logistical scenario. Its distinctive track system further illuminated the unique German engineering philosophy. Unlike the more common designs featuring rubber blocks on a cable, the SD, KFZ 251 employed individual metal track links, meticulously connected by pins, mirroring those found on main battle tanks, but with a narrower profile. Each side incorporated 70 such track links, forged from manganese steel and shaped with specific grooves to enhance grip. These robust tracks exhibited remarkable longevity on firm surfaces and could sustain severe impacts, yet they generated considerable noise. They also caused noticeable surface degradation on paved roads and demanded unremitting adjustment and upkeep. Nevertheless, German designers embraced these compromises, prioritizing the track's superior performance in the most unforgiving environments, such as deep mud, heavy snow, and extreme cold, where rubber components were prone to cracking and catastrophic failure. A significant deviation in German engineering was evident in the SD, KFZ 251's interleaved road wheel system. While most half-tracks, including American variants, typically utilized only 4 or 5 road wheels per side, affixed to straightforward support structures, the SD, KFZ 251 featured 7 overlapping and interwoven road wheels on each flank. These were configured such that wheels from opposing flanks interdigitated, creating a distinct zigzag pattern when viewed from the vehicle's rear. This innovative interleave design facilitated a more uniform weight distribution, additionally lowered the localized pressure on the terrain, and consequently provided a remarkably fluid and comfortable journey for a tracked vehicle. German soldiers who had experienced rides in both captured American half-tracks and their indigenous hanemags unanimously favored the German suspension, attesting to its demonstrable superiority. The significant drawback, however, was that these intricate interleaved wheels constituted a logistical nightmare regarding upkeep. Should an inner wheel sustain damage or require substitution, multiple outer wheels first had to be removed. Furthermore, mud, snow, and ice would accumulate within the wheel system and solidify overnight, a particularly acute problem on the Eastern Front where temperatures frequently plummeted to -40°C. German crews dedicated substantial time each dawn, often spending hours with hammers and blowtorches, simply liberating the frozen components. A routine task that might take a mere 15 minutes on an American half-track could potentially absorb an entire half-day on a hanemag. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The complexity of manufacturing mirrored the intricate nature of its mechanical systems. Constructing an SD, KFZ 251 in 1940 demanded approximately 3,000 man-hours of specialized craftsmanship, a stark contrast to the roughly 800 hours required for an M3 half-track. Germany managed to produce around 15,500 SD, KFZ 251s throughout the entire conflict, a notable achievement given their prevailing industrial circumstances, yet constituting less than a third of the output achieved by American manufacturers. This disparity clearly manifested the national priorities of quality versus quantity, embodied through the tangible forms of steel and rubber components. Subsequently, the narrative takes a dramatic turn as imaginative individuals considered weaponizing these essentially up-armored utility vehicles by integrating heavy ordnance onto their platforms. The concept initially appears audacious until one recalls the fundamental impediment of traditional artillery. Its reliance on trucks or horses for towing meant that deployment consumed an inordinate amount of time. Moreover, rapid relocation to evade retaliatory artillery barrages proved exceedingly difficult. By directly mounting the same gun onto a half-track, a dynamic combat capability emerged, offering swift engagement, rapid repositioning, and enhanced survivability. However, the technical hurdles presented formidable difficulties. The primary engineering challenge revolved around the immense force of recoil, which threatened structural integrity. When a 75 mm gun fired, it produced approximately 15 metric tons of backward thrust in a mere fraction of a second. This energy demanded effective dissipation. Simply bolting a cannon to a half-track's cargo bed would catastrophically disassemble the chassis or invert the entire machine. American engineers, while developing the M3 gun motor carriage, GMC, in early 1941, resolved this issue through a multifaceted strategy. They integrated a French 75 mm gun onto a strengthened mounting platform, which was welded directly to the vehicle's frame rather than its body. Additionally, they incorporated substantial hydraulic damping mechanisms, functioning essentially as advanced shock absorbers, which permitted the gun barrel to slide rearward by about 2 feet upon firing, thereby converting that abrupt 15-ton impulse into a controlled, diffused exertion spread over a full second. Yet, there remained additional physical principles to contend with. In accordance with Newton's third law, every action has an equal and opposite reaction. Consequently, even with sophisticated recoil management, firing still imparted significant motion to the entire chassis. The ingenious solution involved outriggers and spades, retractable metallic supports that swung down from the sides and rear, terminating in flat plates designed to embed themselves firmly into the terrain. Before firing, the crew would activate these anchoring mechanisms, effectively securing the half-track's position. The M12 gun motor carriage, which mounted a powerful 155 mm howitzer on a modified M3 chassis, featured a massive spade at its rear that had to be forcibly entrenched into the earth before each fire mission. Without this crucial stabilization, firing would physically propel the 26-ton apparatus multiple feet rearward with every single shot. The Germans, however, adopted an alternative methodology with their SD, KFZ 251-9 variant, colloquially known as the Stummel. This vehicle integrated a short-barreled 75 mm gun within a restricted rotational mounting system. Instead of endeavoring to create a dedicated self-propelled artillery platform, they fundamentally engineered a close-support assault weapon, a machine capable of advancing alongside infantry, swiftly demolishing fortifications or structures from proximate distances, and then continuing its advance. The limited traverse capability resulted in reduced strain on the vehicle's framework, because the gun was unable to rotate sufficiently to compromise stability. Its maximum elevation was restricted to merely 20 degrees, indicating that this vehicle was not intended for engaging in indirect fire missions over topographical obstacles, but rather for engaging visible objectives with direct line of sight, typically within 800 meters. Ammunition storage presented yet another formidable challenge. A conventional artillery piece might have its ordnance stored in close proximity within a fortified emplacement. On a half-track, however, every single projectile was transported directly aboard the vehicle, which meant that protective plating assumed paramount importance. The M12 GMC, for instance, could carry only 10 rounds of 155 mm ammunition. Internally, primarily because each shell weighed 95 pounds and occupied a considerable volume, these vehicles frequently deployed in conjunction with a dedicated M30 ammunition supply half-track following behind, loaded with an additional 40 rounds. German vehicles encountered analogous limitations. The SD, KFZ 251-9 housed just 52 rounds of 75 mm ammunition, stored within armored compartments situated along the most heavily protected sections of the hull sides. The development of anti-aircraft variants extended the boundaries of vehicular engineering even more profoundly. The American M16 multiple gun motor carriage, for example, integrated a quad mount of .50 caliber heavy machine guns within an electrically powered traversing and elevating system, thereby establishing a dynamic anti-aircraft battery. The entire turret assembly, including its dedicated generator, weighed over a ton, and was positioned significantly above the vehicle's center of mass. Engineers were compelled to incorporate counterweights and slightly widen the track stance to mitigate the risk of capsizing during aggressive maneuvering. The combined rate of fire stood at 2,400 rounds per minute, a figure that appears formidable until one considers that this translates to 200 pounds of ordnance expended every 60 seconds. The M16 carried 5,000 rounds total, granting approximately 2.5 minutes of continuous fire before exhausting its supply, which meant the majority of the internal volume was dedicated to stowing crated, belt-fed ammunition. The pinnacle achievement within this design philosophy was arguably the SD, KFZ 251/22, conceived and deployed by the Germans in the year 1944. This variant mounted a 7.5 cm PaK-40 anti-tank cannon, a formidable weapon capable of penetrating 100 mm of hardened steel protection at 1,000 meters, rendering it a formidable adversary even for the Soviet T-34 tanks. However, integrating such a powerful gun onto a light vehicle necessitated concessions across all aspects of its design. The onboard ordnance supply was reduced to a mere 19 projectiles. The gun's protective mantlet was barely adequate, as more substantial armor would exceed the structural limits of the vehicle's frame, and firing from anything other than perfectly level ground presented a significant danger of overturning the apparatus. Crews developed a meticulous approach to tactical placement, understanding that the initial engagement could very well be their sole opportunity before they had to reposition swiftly or face annihilation from enemy retaliation. Such tank destroyers represented a prime example of engineering born of urgent necessity. By 1942, both the Allied and Axis powers found themselves confronted by armored adversaries for which their existing arsenal was unprepared. German Tiger tanks that rendered the majority of Allied armaments ineffective, Soviet T-34s that decisively breached German fortifications, and Japanese armor in the Pacific that demanded greater destructive power than conventional infantry's small arms offered. The underlying problem was straightforward. The construction of purpose-built tanks consumed substantial time and material assets, which were in short supply for all belligerents. The alternative solution, integrating anti-tank weaponry onto readily available half-track platforms, offered a timeline measured in months rather than a protracted period of years. The American M3 gun motor carriage represented the inaugural, hastily assembled effort, conceived in 1941 prior to the attack on Pearl Harbor. Engineers at the Aberdeen Proving Ground took standard M3 half-tracks, displaced the rearward bench seating arrangements, and integrated a 75mm M1897 cannon, a design originating from the First World War, onto a pedestal within the cargo area. Lacking a traversing turret and substantial armor, the vehicle offered merely a frontal gun shield and relied heavily on fortune. Its 5-person complement remained entirely vulnerable from the waist upward. Nevertheless, what truly mattered was its capability to neutralize German Panzer III and early Panzer IV tanks at a range of 1,000 yards. Impressively, 2,200 units were constructed between 1941 and 1943. These vehicles were deployed operationally in the North African theater starting in November 1942, where American forces at Kasserine Pass gained harsh insights into the qualitative advantage of German armored forces. The M3 GMC's performance in Tunisia underscored the inherent vulnerability of the half-track mounted tank destroyer. It possessed offensive capability but lacked defensive resilience. Its side armor, measuring 6.35 mm, was scarcely sufficient to repel small arms fire, and proved entirely ineffective against more substantial ordnance. German gunners quickly identified M3 GMCs as high-value objectives, understanding that neutralizing one early would eliminate a significant danger. American post-engagement analyses from the battles around Sidi Bouzid in February 1943 indicated that M3 GMCs were compelled to engage from camouflaged emplacements at least 1,200 yards back, leverage their intrinsic maneuverability for continuous relocation, and under no circumstances allow themselves to be exposed in open terrain. They were essentially tactical hunters relying on surprise, rather than direct combatants. The vehicles in question were more akin to cunning hunters than direct combatants, a philosophy that underpinned their development. The Germans, driven by dire exigency on the Eastern Front, conceived their own distinct half-track tank destroyers. By the close of 1943, the sheer volume of Soviet tank production was unequivocally swamping German defensive positions. Initially, the SD, KFZ 251-10 was pressed into service, armed with a 3.7 cm Pak-36, a weapon already considered antiquated and capable of scarcely penetrating the frontal armor of AT-34. Urgently seeking an enhanced capability, German engineers swiftly devised the SD, KFZ 251-22, which incorporated the far more potent 7.5 cm Pak-40, the identical cannon utilized in their purpose-built tank destroyers. Production of this new variant commenced in 1944, with approximately 175 units manufactured before the cessation of hostilities. This improved vehicle possessed the capacity to pose a legitimate menace to Soviet armor, boasting penetration values that could reach an impressive 133 mm at 500 meters when employing standard ammunition, a capability sufficient to punch through AT-34's hull or turret at the majority of typical combat ranges. However, the integration of such a powerful artillery piece onto a half-track chassis inevitably introduced severe compromises. The Pak-40 alone weighed a substantial 1,425 kilograms, exceeding 3,100 pounds. When factoring in the mount, protective shield, and a full complement of ammunition, the total combat load approached 2 tons, a significant burden for a vehicle originally engineered for infantry transport. Consequently, the SD, KFZ 251-22 became notoriously nose-heavy, exhibited poor handling characteristics, and its suspension system was perpetually strained. Its maximum operational speed plummeted to 40 km per hour, and its cross-country performance markedly deteriorated. German crews frequently articulated that driving a fully loaded example was akin to wrestling a stubborn horse, demanding considerable physical exertion for steering, particularly when navigating through challenging conditions like mud or snow. The tactical employment of these vehicles gradually evolved through arduous experience, with both American and German military doctrines emphasizing largely congruent principles by 1944. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. Half-track tank destroyers proved most effective when deployed in carefully prepared defensive positions. In such scenarios, they could leverage topographical features for concealment and cover, interdict adversary armored formations from their furthest effective firing distances, and expeditiously withdraw after engaging. During the major Soviet offensive operation in June 1944, German SD, KFZ 251-22s were typically employed in small groups, generally comprising 3 to 5 vehicles, strategically positioned within tree lines or behind embankments. Their operational procedure involved patiently awaiting Soviet armor columns to approach within 800 meters, unleashing a concentrated volley of fire, and then immediately relocating to pre-designated fallback points. Survival in these engagements hinged critically on superior mobility and the element of surprise, as remaining stationary to prolong a fight invariably meant annihilation. The American experience in France following D-Day revealed comparable methodologies. M3 gun motor carriages, GMCs, bolstered ground troop movements by offering elevated observation and protective fire from ridgelines, standing prepared to counteract German counterattacks. During the intense fighting around St. Lo in July 1944, M3 crews honed their coordination tactics with M10 tank destroyers. The lighter half-tracks would strategically lure enemy armored vehicles into exposing their positions, allowing the heavier, more protected M10s to deliver the decisive blows. This was undeniably dangerous work, frequently resulting in high casualties, yet it proved instrumental in preventing German armored units from unchecked rampage through American infantry positions. Ultimately, the half-track tank destroyer was far from an optimal design. Rather, it represented the expedient answer. It was rapidly manufactured and extensively deployed because the stark alternative was confronting formidable enemy tanks with nothing more than bazookas and sheer audacity. By late 1944, both Allied and Axis forces were gradually decommissioning these platforms in favor of purpose-built armored fighting vehicles. Nevertheless, for 2 critical years, these ad hoc composite platforms filled a critical void, serving as indispensable stopgaps. Stripping away the specialized armaments and the associated glory, one uncovers the half-track's core utility, ensuring the secure and combat-ready delivery of ground troops to the engagement zone. This objective might sound deceptively simple until one delves into the intricate engineering details, for designing an armored personnel carrier necessitates a delicate equilibrium between 3 inherently conflicting attributes: protection, capacity, and mobility. Excessive armor invariably renders the vehicle too ponderous for effective maneuverability. Conversely, carrying too many soldiers compromises vital space for ammunition or essential equipment, and prioritizing speed above all else often means the occupants face catastrophic loss of life upon the first burst of machine gun fire. The M3 half-track's armor scheme illustrates precisely the outcome of these design considerations. Its front plate consisted of 12.7 mm of rolled homogeneous steel, expertly set at a 30 degrees angle. Through the principles of angle ballistic deflection, this provided effective protection equivalent to approximately 15 mm of vertical armor. Such a defense was generally sufficient to halt standard 7.92 mm German rifle rounds at 100 meters, and .30 caliber machine gun fire at most engagement ranges. However, the side armor drastically reduced to 6.35 mm, offering only marginal resistance to pistol rounds and shrapnel, but little else. The rationale for this thinness was pragmatic. Every single millimeter of steel added across the vehicle's 18-foot length equated to a substantial increase in mass. Engineers meticulously calculated that 6.35 mm sides were the absolute minimum required to keep crew and passengers adequately shielded from blast fragments and light-caliber weaponry, while crucially maintaining the vehicle's agility across soft ground. The interior layout was uncompromisingly functional. The driver and vehicle commander occupied the front, seated in separate positions, each with armored access points allowing ingress and egress. Behind them, the cargo area extended roughly 6.5 feet wide by 10 feet long, furnished with bench seats running along each side. 10 infantrymen would sit facing inward, often in close proximity with knees almost touching, their rifles held vertically or laid across their laps. The fundamental reason for this compact configuration was strategic, to ensure soldiers remained positioned below the armored sidewalls. To stand up meant being unshielded from the torso upwards, susceptible to a full spectrum of threats, ranging from rifle fire to shrapnel. Consequently, combat-experienced units quickly learned the imperative of remaining seated until the absolute last moment prior to dismounting. The open-top design remained a perennial contention, both in its time and in contemporary discussions. Why, many asked, was a roof not incorporated? The answer lay in 3 critical factors: weight, visibility, and escape. A steel roof robust enough to provide substantive ballistic defense would have added at least 800 pounds, thereby exceeding the chassis' structural integrity and significantly elevating the contact stress on the terrain. More critically, the infantry squad leader absolutely required an unobstructed view of the surrounding environment during movement. Completely buttoning up would have meant proceeding unknowingly into deadly traps and ambushes. Furthermore, in the catastrophic event of a mine strike or a direct, disabling hit, an open-top ensured soldiers could evacuate with utmost speed, rather than attempting to squeeze through narrow doors while the vehicle was engulfed in flames. The pivotal advancement, however, was the evolution of mechanized infantry doctrine. This is precisely where the half-track redefined military engagement far beyond its mechanical attributes. Prior to 1940, infantry either marched arduously or were transported in unarmored trucks, frequently reaching combat zones in a state of depletion or vulnerability. The half-track introduced a novel operational paradigm. Infantry units now possess the capability to maintain synchronicity with armored formations and arrive at their objectives invigorated and fully prepared to fight. During the North African campaign at El Alamein in October 1942, British and Commonwealth forces effectively utilized American-supplied M3s to follow their armor breakthroughs, capitalizing on breaches in the enemy's lines before opposing forces could redeploy. The infantry reached their destinations invigorated and fully equipped, capable of dismounting and immediately securing objectives that tanks alone could not hold. The Normandy landings on June 6, 1944, further validated the operational philosophy amidst the most challenging circumstances imaginable. American armored divisions employed M3 half-tracks to push inland from the beaches, transporting infantry through the dense bocage terrain, notoriously hazardous for armored vehicles. The standard operating procedure typically involved half-tracks advancing in column behind Sherman tanks, maintaining a distance of 50 to 100 yards. When enemy fire erupted, the Shermans would reciprocate engagement while infantry dismounted from the half-tracks, skillfully utilizing the vehicle's bulk as immediate cover. This entire process, from first contact to infantry on the ground and maneuvering, often took no more than 15 seconds. German after-action reports from Normandy consistently observed how quickly American mechanized units could respond to contact compared to their own truck-mobile infantry, who were compelled to dismount farther back and advance on foot. The numerical data eloquently narrate the extent of their incorporation. A typical United States armored infantry formation in 1944 comprised 3 rifle companies, each with 3 platoons, and each platoon containing 4 squads. This totaled 36 squads, necessitating 36 half-tracks along with their respective command and logistical support units, amounting to roughly 50 half-tracks per battalion. These vehicles did not merely transport personnel, they also carried essential equipment such as .50 caliber machine guns, mortars, ammunition, radios, and medical supplies. The half-track profoundly altered the tempo and adaptability of mechanized warfare, effectively converting ground troops from traditional marchers into mobile fighting forces. By 1945, the pertinent question was no longer whether to mechanize infantry, but rather how to engineer the subsequent generation of vehicles that could execute this role with even greater efficacy. To take a machine meticulously designed in Cleveland for the battlefields of Europe, and then deploy it into the brutal Russian winter or the suffocating Pacific jungles was to witness each foundational design premise unravel. The half-track's ultimate crucible lay not in controlled testing facilities in Maryland, but rather in the -40 mornings outside Stalingrad and the 100% humidity jungle trails of New Guinea. These extreme environments compelled on-site adaptations unforeseen by the original designers, leading to the creation of variants that scarcely maintained the visual characteristics of their initial configuration. The Eastern Front was where theoretical design confronted brutal operational conditions, with devastating consequences. German SD, KFC 251s began experiencing severe operational incapacitation during the winter of 1941 to 1942 as Army Group Center pressed its advance toward Moscow. The otherwise sophisticated interleaved road wheels, which provided such smooth rides in temperate conditions, became lethal impediments when mud froze solid overnight between the wheels. Crews resorted to every conceivable measure, lighting fires underneath vehicles, pouring vital fuel reserves between the wheels and igniting it, and even employing explosive charges to blast ice free. Crucially, no single method yielded reliable results consistently. German field workshops soon began welding steel plates over the gaps between the wheels, a modification that diminished operational efficiency yet effectively mitigated the problem of ice buildup. By late 1942, factory production lines incorporated wider wheel spacing and a simplified suspension design specifically tailored for Eastern Front units. American M3 half-tracks, delivered to the Soviet Union under the Lend-Lease program, encountered a distinct array of operational challenges. Between 1942 and 1945, approximately 1,100 M2 and M3 variants reached Russian hands, prompting immediate and inventive modifications by Soviet mechanics. A primary concern revolved around their cold start capability. The Hercules engine's carburetor was prone to severe icing in sub-zero temperatures, rendering ignition impossible without extensive preheating. To counteract this, Soviet workshops ingeniously fitted engine block heaters, insulated fuel lines, and adapted carburetors with adjusted jet sizes to accommodate the thicker, cold-affected gasoline. Furthermore, they constructed rudimentary yet highly effective wooden enclosures over the open cargo compartments, transforming these personnel carriers into makeshift armored vehicles that offered vital protection against the biting wind chill during protracted troop movements across the vast Eastern Front. The performance of tracks in deep snow presented another formidable obstacle, necessitating radical engineering solutions. The standard rubber block tracks would invariably accumulate snow, which then compacted into solid ice, leading to a complete loss of traction. Both German and Soviet forces independently experimented with grousers, which were robust metal cleats designed to be bolted onto the track blocks, allowing them to dig into snow and ice much like mountaineering crampons. The Germans, in particular, devised a comprehensive winter kit comprising special track extensions that significantly augmented the surface area by almost 40%. This innovation dramatically reduced ground pressure, enabling their vehicles to traverse snowdrifts that would otherwise engulf conventional wheeled transport. While installing these modifications demanded many hours of arduous labor in frigid conditions, units that neglected to equip their vehicles before launching winter offensives frequently found themselves immobilized and ineffective within a matter of days. Conversely, the Pacific Theater confronted military forces with diametrically opposed yet equally brutal environmental hurdles. Intense heat and pervasive humidity wreaked havoc on sensitive electrical systems, accelerated the corrosion of metal components, and transformed vehicle interiors into sweltering compartments where occupants could succumb to heat exhaustion in mere minutes. American forces deployed to New Guinea, commencing in 1943, faced an unforgiving landscape of dense jungles, treacherous narrow trails, expansive swamps, and numerous unbridged rivers, where the utility of half-tracks initially seemed questionable. Yet, resourceful Marine and Army units uncovered innovative applications for these vehicles. Engineers undertook a drastic modification, entirely removing the front wheels from some M3s and extending the track assemblies forward. This conversion created fully tracked vehicles with a much lower ground pressure, proving invaluable for navigating the deep mud and watery expanses of swamps. These field-modified behemoths, despite their bizarre appearance, possessed an uncanny ability to conquer terrain that rendered all other vehicles immobile. After 2 or 3 paragraphs, stay with us and watch the end of the video. We will be grateful for your like and subscription. In the comments below, let us know where you are from and what you think about the video topic. During the Philippines campaign of 1944 to 1945, Japanese forces encountered American half-tracks for the first time and were genuinely perplexed by their design and tactical role. Japanese military doctrine placed a strong emphasis on light tanks and infantry transported by trucks, leading them to perceive half-tracks as unnecessarily complex and demanding in terms of maintenance. Their assessment was not entirely unfounded, as the intricate American and German half-tracks indeed required unceasing upkeep in tropical climates. The relentless humidity caused electrical connections to corrode rapidly, while the ubiquitous jungle mud infiltrated every bearing and joint. Furthermore, organic debris frequently clogged cooling systems, exacerbating operational difficulties. Consequently, units deployed in these challenging environments were compelled to implement rigorous twice-daily maintenance routines, effectively necessitating the rebuilding of critical systems every few weeks to ensure continued functionality. The chronicles of captured vehicles reveal fascinating narratives of improvisation and adaptation. Soviet forces, for instance, seized hundreds of German SD, KFZ, 251 half-tracks during their major offensives of 1943 to 1944. Despite facing acute shortages of ammunition and spare parts, these vehicles were immediately pressed into service. Soviet crews ingeniously welded on supplementary armor plates salvaged from destroyed tanks, creating formidable, if somewhat ponderous and slower, Frankenstein vehicles with enhanced protection. Some Soviet-operated Hanemags underwent even more radical transformations, receiving entirely new armaments such as 85mm recoilless rifles, Katyusha rocket rails, and even flamethrowers. While these alterations would undoubtedly have appalled the original German engineers, Soviet military doctrine consistently prioritized maximum firepower and combat effectiveness over strict mechanical purity or original design integrity. Operations in the North African desert demanded yet another distinct set of modifications. The pervasive fine sand infiltrated every mechanical component, drastically accelerating engine wear and reducing their operational lifespan to a mere fraction of what was considered normal. British forces, utilizing American M3s during the Western Desert Campaign from late 1942 onwards, installed enormous air filters, some towering nearly 3 feet high, specifically to safeguard engines from the relentless ingestion of sand. They also replaced the standard tracks with desert pattern variants featuring wider blocks, which provided superior flotation and mobility in the soft, shifting sands. Water, both for vehicles and crews, became an absolutely critical logistical consideration. Vehicles operating in the vast Sahara Desert carried additional radiator coolant and frequently towed trailers laden solely with water cans. The overarching lesson gleaned from these myriad adaptations was profound. The half-track was not a singular, monolithic vehicle, but rather a versatile platform that spawned dozens of specialized variants, each meticulously evolved to endure the specific, hellish environments that would have rendered the factory standard version inoperable within weeks. By 1946, a vast inventory of thousands of half-tracks lay dormant in motor pools stretching from Fort Knox in the United States to Frankfurt in Germany. Military planners grappled with an uncomfortable, pressing question: what was to be done with these machines? The global conflict had concluded, and in the stark, unsparing clarity of peacetime analysis, the inherent compromises of the Halftrack's design became impossible to disregard. It occupied an awkward middle ground, being neither a fully capable truck nor a true tank. In the context of the emerging Cold War landscape, this ambiguous tactical niche suddenly appeared to be a strategic dead zone, lacking clear utility for future conflicts. The Korean War, spanning from 1950 to 1953, was anticipated to be the Halftrack's triumphant return to prominence. American forces dispatched M3s to the Korean peninsula, fully expecting them to replicate their successful performance from the European theater. Instead, the Korean conflict mercilessly exposed every underlying weakness that the exigencies of wartime urgency had previously obscured. The brutally mountainous terrain of Korea relentlessly shredded transmissions and suspensions that had been engineered for the comparatively smoother roads of Europe. The rubber track blocks, which had proven adequately functional in France, rapidly disintegrated on the unforgiving Korean granite, often failing after traversing a mere 400 meters before necessitating replacement. Maintenance requirements escalated to absurd levels. A single M3 demanded approximately 40 man-hours of upkeep per week just to remain operational, a stark contrast to the roughly 10 hours required for a typical truck. Faced with these overwhelming logistical burdens, commanders increasingly opted to leave half-tracks in motor pools, instead requisitioning more reliable and less demanding trucks. However, the most decisive factor in the half-track's decline was a fundamental tactical mismatch. Warfare in Korea featured unexpectedly longer engagement ranges, with infantry battles frequently unfolding at distances of 600 to 800 yards, a significant departure from the close-quarters hedgerow fighting prevalent in Normandy. The half-track 6.35 mm side armor, which in 1944 offered only marginal protection against rifle rounds, proved utterly inadequate against the Soviet-supplied weaponry employed by North Korean and Chinese forces by 1951. Even the 7.62 by 25 mm rounds from a PPSH-41 submachine gun could penetrate these thin sides at 200 yards, while heavy machine guns effortlessly transformed half-tracks into riddled metal shells. Commanders swiftly recognized that deploying M3s anywhere near the front lines invariably resulted in catastrophic casualties among their soldiers. Concurrently, military engineers were conceptualizing and designing a truly innovative successor. The M113 Armored Personnel Carrier, which emerged from the Ordnance Tank Automotive Command in 1956, embodied everything the half-track was not. It was a fully tracked vehicle, eschewing the hybrid design. Its armor was made of lightweight aluminum rather than heavy steel, providing comparable protection at half the weight, and it possessed inherent amphibious capabilities. Most critically, the M113 was conceived and designed from the ground up specifically as a personnel carrier, rather than being an adaptation of an existing truck chassis. This revolutionary vehicle could effortlessly swim across rivers, offered significantly improved survivability against mine blasts compared to half-tracks, and its lower profile presented a smaller target to enemy fire. The initial production units rolled off assembly lines in 1960, and by 1963, the undeniable writing was on the wall. This new platform unequivocally represented the future of armored troop transport. The underlying engineering philosophy had undergone a complete paradigm shift. Half-tracks were emblematic of 1930s thinking, characterized by the approach of taking proven truck technology, adding tracks, and optimistically hoping the combination would prove effective. The M113, by contrast, epitomized modern systems engineering, starting with a comprehensive understanding of mission requirements, meticulously designing every component to function cohesively, and rigorously optimizing the entire system for the actual combat environment it would face. The M113's Detroit Diesel 6V53 engine generated 215 horsepower, nearly 50% more power than the venerable Hercules engine, while simultaneously weighing less and operating on safer, more efficient diesel fuel instead of gasoline. Furthermore, its advanced torsion bar suspension system delivered superior ride quality and demanded considerably less maintenance than the Halftrack's vertical coil springs. Ultimately, a thorough cost analysis delivered the final, decisive blow. By the early 1960s, the expense of maintaining the dwindling number of Halftracks remaining in the U.S. military inventory had surpassed the cost per vehicle mile of acquiring brand-new M113s. Spare parts for the aging Halftracks were becoming increasingly scarce, given that their production had ceased in 1945. Furthermore, the generation of mechanics intimately familiar with the intricacies of the old white motor transmissions was steadily retiring. In stark contrast, M113 production was rapidly accelerating, leveraging modern manufacturing techniques that drove per unit costs below $40,000. While this was a substantial sum in 1960, it represented a far more economically sound investment compared to the escalating costs of keeping 15-year-old, obsolete vehicles operational. The international market echoed this conclusive narrative of obsolescence. Israel, for instance, acquired hundreds of surplus American Halftracks in the 1950s and utilized them extensively through the 1967 Six-Day War. However, even the Israeli Defense Forces were in the process of transitioning to purpose-built armored personnel carriers by the 1970s. Soviet forces, after World War II, entirely abandoned half-track designs, making a direct leap to fully tracked APCs such as the BTR-50. The French military retained their half-tracks for the longest duration, operating some into the 1970s during various colonial conflicts, primarily due to financial constraints that precluded a wholesale replacement of their armored vehicle fleet. The demise of the half-track was not attributable to outright battlefield failure. These machines generally performed adequately within the context of their era. Rather, their obsolescence was a consequence of relentless military evolution. Modern warfare progressed at a faster pace, delivered harder impacts, and increasingly demanded specialized, purpose-built solutions instead of versatile compromises. The M113 and its subsequent generations offered a multitude of superior capabilities. They could swim across water obstacles, provided crucial nuclear, biological, chemical, NBC, protection, mounted heavier weapon systems, and, most importantly, significantly enhanced the survivability of infantry in an age characterized by ubiquitous automatic weapons and devastating artillery fire. By 1970, virtually every leading military power had arrived at the same unequivocal conclusion: choose either tracks or wheels, but the hybrid era was definitively over. The final American half-tracks were retired from active service around 1964, bringing an end to their 23-year operational history. The year 1964 marked a significant turning point, bringing to a close a remarkable 23-year operational span for a particular type of military transport. This date signaled the end of an era for the iconic half-track, a vehicle that had played a crucial role in various global conflicts and logistical operations. Its departure from active service represented a shift in military doctrine and technological advancements, as newer, more specialized armored personnel carriers began to supersede its versatile, yet ultimately compromised, design. The retirement of these venerable machines in 1964, after more than 2 decades of service, underscored the relentless evolution of military hardware and the constant quest for improved mobility and protection on the battlefield. Following their formal retirement from primary combat roles, many of these robust vehicles were repurposed, embarking on entirely new careers. A considerable number were ingeniously converted into specialized engineering vehicles, demonstrating their adaptability by assisting in construction and demolition tasks. Others found utility as resilient recovery trucks, capable of extracting disabled equipment from challenging terrains, or as mobile command posts, providing essential communication and coordination hubs in tactical environments. However, the quintessential configuration, that of a troop transport designed for frontline deployment, progressively vanished from active military formations. This marked a definitive end to their pervasive presence in forward operating areas, a stark contrast to their widespread use during their peak. In the contemporary landscape, the dwindling number of operational half-tracks exists primarily as historical artifacts, carefully preserved within the hallowed halls of military museums or cherished within exclusive private collections. They stand as veritable mechanical fossils, silent testaments to a bygone era when engineering visionaries harbored the ambitious, perhaps even audacious, belief that it was feasible to construct a single vehicle capable of fulfilling every conceivable operational requirement. This grand aspiration, however, ultimately proved elusive. A truly universal military vehicle remained beyond reach. Yet, for a critical and intensely demanding decade, a period characterized by urgent global needs for rapid troop deployment and mobile infantry, the half-track's inherently imperfect, yet remarkably effective, compromise offered precisely the solution that was desperately required. Its blend of wheeled speed and track traction, while not flawless, was sufficient to meet the pressing demands of the time, making it an indispensable asset when the world demanded immediate and decisive action. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic.